Hi everybody, and welcome to tonight's video where we are going to be talking about quadratic functions. This is going to be a mix of kind of like review from what we've already talked about this year and what you talked about in your Algebra 2 class, and also some new stuff in terms of how we are going to be looking at things, or maybe what kind of information we want versus what we're used to doing with these different functions. So first of all, what are quadratic functions? They are any function of the form f of x equals ax squared plus bx plus c, where a, b, and c are going to be real numbers. Okay, we've seen this before. You've probably worked with the quadratic function in this form as well, but take a second to think back on what we already know about quadratic functions. All right, we've referred to these as square functions. So if you look in your packet from the last chapter where we had our family of functions, it was f of x equals x squared, right? That was the most basic quadratic function, or the most basic square function. Now we're going to be talking about ones that are a little more complicated. There's more to the equation, but we've already seen that as well in terms of our transformed version of the square function, where we had f of x equals a times x minus h squared plus k. So this a is the same a that we see right here. The h and k, we're going to show you how to determine those given the a, b, and c in a little bit. But I want you to keep in mind that all of this stuff basically is interchangeable. It's all related. It's all talking about the same function, the same kind of function. If we have a quadratic function, we know that it's some interpretation of this most basic form, this most basic parabola. And we've already talked about how we can take a basic parabola and move it around, flip it around. A tells us if it's opening up or down, if it's wider or skinnier. H tells us if it's moved left or right, and K tells us if it's moved up or down. Right, so we've already talked about and played with all these different functions and different transformations. For now, though, instead of using all of this, we're going to put that off to the side, keeping in mind what we already know about quadratic functions, and now we're going to take a different approach to them. We're going to look at them using this standard form, right? This ax squared plus bx plus c. This h and k will come back into play in a few minutes, but keeping in mind, we're just thinking about how to go from this to a graph, or these different parts, to identify these different parts of the graph of the parabola. So first of all, let's take a look at these. So every graph of a quadratic function is going to be a parabola, and each parabola has these four parts. The first part is that we have what's called the axis of symmetry, and this is going to be a vertical line. And so off to the side here, I'm looking at this standard parabola. The vertical line, this axis of symmetry, is this line that cuts it in half, right? So the parabola is symmetric on each side of this line. And when we talk about this graphically in the next video, we're going to see how convenient it is for helping us graph a parabola, but we'll get to that later. The next thing that we talk about, the next part of a parabola, is something that's called the vertex, and the vertex is a point. We've already referred to this. It's the minimum or maximum value, right, of the parabola. And what's nice about the vertex and the axis of symmetry is that the axis of symmetry goes right through the vertex. So this vertex is this point right here. The y-intercept is going to be 1 point, and it's going to be where the parabola crosses the y-axis. So if I set up a coordinate plane here, and let's say I have my parabola that looks like this, the y-intercept is going to be this single point where it crosses the y-axis. So here's my y-axis, and that's where the parabola crosses it, so there's my y-intercept. Now, the x-intercepts, the x-intercept is going to be a point or points, right? So I'll put the s in parentheses. In this case, the way that I have it drawn here, the x-intercepts are, there's two of them. There's 2 points where it crosses the x-axis. But let's extend this x-axis a little bit. There's other ways that a parabola can be drawn, right? So I could have a parabola that looks like this, where it intersects the x-axis at exactly one point, and that's the vertex, right? So if the parabola is just sitting on the x-axis, there's only one x-intercept, one point where it intersects. And remember, these could be opening up or down, doesn't matter. So it could be sitting on the x-axis and opening down, or sitting on the x-axis and opening up. And then the other option that I could have, or I could see, a parabola that's drawn like this, where it's located above the x-axis and it opens up, right? And so in that case, it never crosses the x-axis, so there's no x-intercept. Here, I could have the same thing. I could have a parabola that's opening down and below the x-axis, so it never crosses. Now, it might not look like these ones have y-intercepts either, but they do, because remember, this arrow is going down, so the y-intercept will be way down here somewhere. Same thing with this one. It'll be way down here, or this one will be way up there. But just because you don't see the y-intercept, know that we always have one of those. The x-intercept, it is possible to have 0, 1, or 2 of those, right? So that could be different. But the y-intercept, there's always one. So even though it might not look like there is one, there is a y-intercept. But here, it doesn't look like there's an x-intercept, and that's true, there isn't one either. Okay, so just keep in mind that it might not always look like there are y-intercepts, but there are. In the case with the x-intercept, it might not look like there is one, and that's possible. It could be true that there's not. So, vertical line, and then points. We can determine these graphically, which I kind of alluded to right here, but we'll get more detail later. But what we're going to do today is determine them algebraically. So that's our next example, determining the parts of the graph of a quadratic function algebraically. Okay, and let's do an example with this. We'll demonstrate all of these with an example, and we'll say that we have f of x equals negative 2x squared plus 8x plus 10. Now, before I do anything, I'm going to want to identify, in this case, what are a, b, and c. And remember, if f of x is in standard form, it's ax squared plus bx plus c. So I can match up a, b, and c here. So a, in this case, is negative 2. It's a coefficient with the x squared term. B, in this case, is 8. And c, in this case, is the constant term that's by itself on the end, and that's going to be 10. Now, this a, b, and c is going to help us find these four things: the axis of symmetry, the vertex, the y-intercept, and the x-intercepts. So first, let's start with our axis of symmetry. And so the axis of symmetry is a vertical line, which we mentioned on the previous page. And a vertical line is always of the form x equals some constant or some number, right? That's the equation of a vertical line. It's x equals some number, right? So whatever the x coordinate is, that's the x coordinate for every point on that line. So we can define that line by just saying x equals some number. In this case, for any parabola, the axis of symmetry is the equation x equals negative b over 2a. So if I know what b and a are, I plug it in here. So x equals, in this case, the opposite of 8, so negative 8 over 2a, so 2 times negative 2. So I get negative 8 over 2 times negative 2 is negative 4. Negative over negative is positive. 8 over 4 is 2. So the axis of symmetry for the graph of this function is a vertical line at x equals 2. And I'm going to save off graphing this for a later example. Right now, I just want us to be able to find algebraically what this axis of symmetry is. So here, the axis of symmetry is x equals 2. Now, conveniently, when I get down to the vertex, it's this point, right? It's a point, and the coordinates of the point are h, comma, k. And that's the same hk that we've seen in the transformed form. But how do I get from standard form to this transform form? How do I figure out what h and k are given a, b, and c? The way that I do that is that h equals negative b over 2a and k equals f of h. So this makes sense from what we drew in on the previous page. The vertex is a point, and it's a point where the axis of symmetry crosses the parabola. So the x-coordinate of that point is on the axis of symmetry. So if I've already determined the axis of symmetry, I've determined all x-coordinates of any point that's on that line. So I've already figured out what h is, right? I've already figured out what negative b over 2a is. So here I can say h equals 2. And now the vertex, right, is a point. And a point is always represented by x and the function value of that x. So if h is negative b over 2a, that's the x-coordinate. K is going to be f of h. So I figure out what h is. I've already done that from step number 1. Now all I have to do is plug that into my function to find out what k is. So h equals 2, k equals f of 2. And I can plug that into my original function. So that's negative 2 times 2 squared plus 8 times 2 plus 10. Now I would just evaluate that. So I have negative 2 times 4 plus 16 plus 10. So I have negative 8 plus 26. And so that's going to be 18. So this vertex, this point, is 2, 18. So that is the vertex of my parabola. All right, moving on, the y-intercept. Again, this is also a point, and it's a point where the x-coordinate is 0, right? That's the definition of a y-intercept. It's right along the y-axis, so the x-coordinate is always 0, and the y-coordinate is going to be, therefore, f of 0. So it's wherever I plug in 0 to my function, right? Now looking back up at our function, if I plug in 0 for x, that would cancel out this first term, and it would also cancel out this middle term. So f of 0 would only be whatever is left, which is going to be c, is going to be that constant term. So the y-intercept is always this point 0, c. So it's pretty easy to determine from our equation. In this case, the y-intercept is 0, 10, right? So our y-intercept here is 0, 10, and it's as easy as that. So really, so far, the only work that I've really had to do was to find the axis of symmetry. I plug in negative b over 2a for x, and I evaluate that. That gives me the x-coordinate for my vertex, and so that part's already done. Then I just plug it into the function, so I evaluate f of 2, and so that gives me k. So that part's done. I have my vertex. And now the y-intercept is really simple. It's just essentially the point 0, c, which is 10. And again, I'll talk about interpreting all of this in terms of the graph in a video tomorrow. The last thing we want to talk about here are the x-intercepts. So we mentioned there's 0, 1, or 2, depending on what this graph looks like, where it intersects the x-axis, if it's opening up, down, or if it's on or above or below the x-axis. So to determine how many there are, we are going to figure out what the value of b squared minus 4ac is. So that expression is very important. If b squared minus 4ac is less than 0, then there are 0 x-intercepts. If b squared minus 4ac equals 0, then there is 1 x-intercept. And if b squared minus 4ac is greater than 0 or positive, then there are 2 x-intercepts. Okay, so how many intercepts are there? Determine the value of b squared minus 4ac. So in our case, b is 8, and then a is -2, and c is 10. So b squared minus 4ac, b squared is 8 squared minus 4 times -2 times 10. So 8 squared is 64 minus 4 times -2 is -8 times 10. So I have 64 minus -8 times 10 would be -80. So minus a negative is really positive. So 64 plus 80 is 144. So b squared minus 4ac is 144. That's positive. That's greater than, forgot the c. It's greater than 0. So that means there's going to be 2 x-intercepts. So that's how I know I have 2 x-intercepts by determining this value, b squared minus 4ac. Now, what are the actual intercepts? We are going to use something called the quadratic formula, which I think you should already know. And that is the x-intercepts equal the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And again, conveniently, what we've done in this step helps us figure out our next step. So down here, I have b squared minus 4ac. That's what goes underneath the radical. So now I've already got that part filled in partially for me. So for this equation, x equals the opposite of b, so the opposite of 8, plus or minus, right? That plus or minus, that's how I'm going to determine my 2 x-intercepts. Plus or minus 144, right? I've already determined what b squared minus 4ac is. It's 144, right? So that's what I can just plug in underneath the radical, all over 2 times a, which in this case is -2. All right, so I evaluate this. You can split this apart in this step because you have -8 plus the square root of 144, which is 12, over 2 times -2, which is -4. And you have x equals, the x-intercept equals -8 minus 12 over -4, right? So I split apart the plus and minus. And last step here, -8 plus 12 is going to be 4 over -4, which evaluates to be -1. And over here, -8 minus 12 is -20 over -4. Negative over negative is +5. So remember, these are x-intercepts. These are points where the y-coordinate is 0. So I have the point -1, 0, and 5, 0 as my x-intercepts. So that's how I would determine all of these values algebraically. So use this example to guide you through determining the axis of symmetry, the vertex, the y-intercept, and the x-intercept for this function. F of x equals x squared plus 2x minus 8. I want you to bring that with you to class tomorrow. So use our previous example as a guide to determine these 4 things. And I will help you get started by saying that a equals 1, b equals 2, and c equals -8. Those are the values for a, b, and c that you'll use for this function, and you can figure out those 4 things from there. And bring that with you to class tomorrow, and I'll see you there.